Well, hello everybody. It's time to start. I hope you're all doing well. I'm coming from you again from home. Um, I wanted to encourage you to don't be shy about asking questions or interrupting me. Probably the best way would be to just unmute yourself and speak up. That way, I don't have to look for chat or raised hand. But if you want to just raise your hand or chat, that's fine too. But please don't be afraid to ask questions. It actually helps me a lot to know if you're confused by anything or if I'm going too fast or maybe even too slow. Okay. So I'm going to kind of continue where we were last time. Last time we were talking about parallelism, and I think we'll finish that up, and then we'll start a large design example today. So let me find where we were. So we're somewhere around here last time. So I'm gonna, oh, you probably just don't see that. Let me share my screen. Play that. Okay, so we're talking about parallelism, and this is kind of a unique thing about hardware design versus software is that in hardware design, we get to do things in parallel. We can do more than one thing at a time because we take in, space on the FPGA or space on the ASIC die to implement more than one function. And so multiple functions can run in parallel. So an example of that was the simple grade calculation that I showed you last time. And the kind of the most parallel way to do this is to expand all the multiplies spatially. So we have a dedicated multiply for each multiply operator that's in the equation, and likewise for the plus operators, right? So this is kind of an expensive implementation in the sense that it would take 4 dedicated multipliers and 3 dedicated adders, but it would get the result fairly quickly. And in the delay associated with a multiply and add and another add, we would get a result. Versus some other implementation that would be possibly less parallel and would maybe be cheaper, but it would take more time. So in fact, this idea of doing things in parallel really means we kind of expand the computation spatially. Right? The other thing we can do is expand the calculation temporally into the time domain, and that means we can make it sequential. So really what we do here when we do optimization or we look for ways to parallelize or not is to make trade-offs to kind of move computation between space and time. Right? The kind of ultimate moving it into time is what I showed on this next slide here where we're talking about time multiplexing. And here we take the same computation, but we can do it sequentially. We can do it in time rather than in space. So we have a single operator or piece of hardware that can implement the operators. In this case, I called it an ALU. And we're assuming that this ALU can either do the plus operation or the times operation. And then we kind of reuse that, time multiplex that over the course of multiple cycles in order to execute this little control action that by doing this, we will have computed that grade calculation. Okay, so in that case, we can kind of think of our original implementation, our parallel implementation could be thought of just as an abstract computation graph. It shows us the computation that needs to be done, and then we could do a direct implementation of that, or we could do a temporal implementation of that, or something in between. Right? So that's kind of the nice thing about hardware design is we get to play with the amount of parallelism, and this gives us a way to trade off cost and performance, and also energy. So if we look at this this solution here, it's kind of it reminds you of a software solution. This is kind of like a little program that we're executing here. That's the action of the controller. So it gets us to think about the differences between hardware and software. And this time multiplexed ALU approach is very similar to what you would see if you just wrote a program for a processor. Right? So if you took our RISC-V processor, you could implement the same function by doing some adds and multiplies, and it would do one operation, or would initiate one operation per cycle. So in fact, the CPU is kind of what it does is time multiplex the function of the function units in the processor that we built. We had a single function unit, a single ALU, and it's used for each instruction once per clock cycle. Right? So that's kind of gives us the same idea as that we time multiplex the ALU. The difference with a CPU is that it's programmable. We can change the program that it runs each time, as opposed to this dedicated piece of hardware that I had on my last slide, where this is dedicated to do that grade calculation. Right. So, so this model, this kind of sequential model, it kind of matches our tendency to express computation sequentially. Right. Even though most computations have some degree of parallelism, the programming languages that we use, the traditional ones that we think about, like Java and Python and C and C++, they tend to be sequential languages. They may have some extensions to them that allow you to express parallelism, but they have a sequential default. It's kind of the way they're designed. And it kind of naturally matches the way we think about calculations. We think about doing one thing and then doing another thing and then doing another thing, right? And maybe that natural tendency is just the way we learn, because of the way we learn. It's interesting to think about, can we really naturally think about parallelism? Now, maybe, it's better to think about programs as computation graphs, right? And then this would lead to a wider range of implementations. We could go directly from the computation graph into a parallel hardware implementation. And if we wanted a serial software implementation, we could turn it into a program, right? And in fact, it's easier to sequentialize or serialize a computation graph than it is to extract parallelism from a sequential program. And a lot of people and researchers have spent a lot of time trying to build compilers or other tools that can automatically extract parallelism, and it's difficult. In fact, modern superscalar processors automatically extract parallelism at the instruction level. Right? In fact, a lot of the hardware is in the superscalar processor is in there to extract parallelism from the instruction stream. This is something you can learn more about if you take 152. So, okay, so that's kind of my little story about hardware versus software. A lot of the things that we build in hardware, we start out with a representation that is naturally parallel. For instance, here's a description of a video codec. This is a thing that compresses the video, and you can see it has a variety of blocks here, and the video frames kind of move through these blocks, and this is a natural way to express this sort of algorithm. And if you think about a hardware implementation, you could have dedicated hardware for each one of these blocks, right? So all the blocks could run in parallel. Or you could have a kind of a super block engine that could be time multiplexed to do the action of any of these blocks. Right. So the fully parallel one would be higher performance and would have a higher frame rate and be more expensive. And then the one that time multiplexed some computational engine would be cheaper, but it would have lower performance. Furthermore, within each block here, there's loops, and we could unroll these loops. We could do multiple iterations of the loop at the same point at the same time, right? And I'll talk a little more about that later. Okay, so kind of gets to the idea of talking about loops and optimizing iterative computations. So again, we're kind of looking for opportunities to perform optimization, to provide kind of opportunities for trade-offs between cost and performance. Going back to the very first lecture where we're talking about that is our job as hardware designers, to understand how to optimize the design once we have a correct function, right? So a good place to look is loops, and it's because I claim that hardware implementations of computations almost always include looping, right? Is this true in software? It's probably true. Most of the programs we write have some loops. Maybe there's a throwaway code, something you write, little piece of maybe Python code to compute something for you, and it doesn't iterate. But almost always there's iteration. As far as the hardware, we probably wouldn't bother building such a thing into hardware. A program that didn't have loops, or an algorithm that didn't have loops, we probably wouldn't put it into hardware because you wouldn't build a chip just to run something one time, right? You build chips because you're going to do something over and over again many times. Right? FPGAs could change this. I mean, you could program an FPGA to do a computation just once. But, you know, most of the time, almost always, we're going to have loops. So it's good to look at loops. So why do we have loops? And, you know, this is an interesting thing to think about too. Well, if you think about the types of loops that come up in computations that we do, we have looping over input data. For instance, what we refer to as streaming computation. This usually comes up in media processing, like audio or video processing, because you have a stream of frames in your video, you have a stream of samples in your audio. And there's some computation associated with rendering those or compressing those or, you know, transmitting those, right? So you just kind of loop over the input data. And then there's looping over memory data in memory. For instance, an inner product calculation, right? Where you take two vectors and you multiply them together and add all the products together, or a matrix multiply, right? Where you're multiplying a row times a column and you're iterating over the elements of the matrix or of the vector in memory, or some kind of list processing where you're following pointers, perhaps. Right. So my claim is it's okay. So those are popular ways that we see loops in computations in software and also in hardware, as it turns out. 1 and 2 are really very similar. In fact, we often term media processing into this iterating in memory, right? Because what we do is we load the media into a buffer or an array in memory, and then we process it one buffer full at a time, right? So this is the way to kind of match the high rate of the processor to the slower rate of the input or output of the media. Right? So that's 1 and 2. Number 3 is CPUs. If you think about a CPU, the hardware there is really just executing one loop. It does an instruction fetch, and we do instruction execute, and then instruction fetch, and then execute, and just going over and over again, looping through your program, right? Through the use of the program counter. The personality changes on each iteration, so it's not each time the body of the loop is different, but the body of the loop is really determined by which instruction we're executing, right? So that's another instance. And I think that's all there is. I don't know. If somebody has ideas on where other kinds of loops, I'd love to hear about it, but I think that's pretty much it. Right? So that characterizes why we have loops. So the reason I'm spending so much time talking about loops or iterative computation is that loops offer opportunity for parallelism by executing more than one iteration at once, right? Because we're going to do the loop over and over again, we can think about doing more than one iteration at a time, right? And how do we do that? Well, we can do parallel iteration execution, right? Where we call that loop unrolling. We unroll the loop and do more than one iteration at once. And or we do pipelining, right? So if you think about the processor and if you think of that as being in some sort of iteration, we can take the body of that iteration, which is the execution of the each instruction, and we can pipeline it. So that way we get to overlap more than one instruction at a time. We effectively overlap more than one iteration of the loop at a time, right? So we get parallelism that way. So both those things come up. So we've got opportunities to get parallelism by looking at loops. Okay, so that's why we look at loops. Okay, so mentioned 2 things here: parallel iteration and pipelining. We're going to focus mainly on pipelining. Okay, I'll talk about the other a little later. Okay, So pipeline, this should be a review because you've seen pipelining elsewhere, and we already talked about pipelining when we talked about the RISC-V implementation. But just to sort of reiterate this and review a little bit, when we use pipelining to improve performance in some way, but in the case of pipelining, this comes up when we're less interested in latency and more interested in loop execution rate or throughput. Right? And these two are really, they're different. So here's a review from 61C, or perhaps from another one of your classes. This is the classic analogy that Dave Patterson and John Hennessy made in their book, using washing of clothes to represent pipelining. So when you wash clothes, you put them in the washing machine, and that takes about 20 minutes. And then you put them in the dryer, and that takes about 20 minutes. And then you fold them up, and it takes maybe 20 minutes, right? So each load of wash, if you're going to do a load of wash, it would take you 60 minutes. So if you have 4 loads times 60 minutes, it would take 4 hours if you do it one load at a time. But of course, once you, as shown down here in this little chart, once the washing machine is done, it's free, and you can put the second load of wash in the washing machine. At the same time, the first load can move into the dryer. And then after 20 more minutes, the washing machine is free again, because 2 is done with it, and 2 can move into the dryer. At the same time, you can start folding 3, and then you can put the third load into the washing machine. And we just continue this process until we're done with the washer after 4 loads, and then we kind of drain the pipeline. So kind of fill the pipeline here at the beginning. We're in some steady state period here, and then we drain the pipeline. So in this overlapped version of the washing machine, washing loads, 4 loads, we can do 4 loads in 2 hours instead of 4 hours total. And we're not actually totally efficient. The efficiency goes up if we have more loads to do. More loads of wash to do. So this is obviously the way we would do it. It's very intuitive, and it kind of demonstrates the concept of pipelining. So if you look at this, in the limit, as we increase the number of loads, as I said, it gets more and more efficient, and it gets to the point where the average time per load approaches 20 minutes. One load is completed every 20 minutes. Every 20 minutes we put a new load in, and every 20 minutes we'd be completely done folding, and everything would be done with one load, right? So that means the average time per load is 20 minutes. So the latency actually is still the same. It's still 60 minutes, right? Because we have to do the washing, the drying, and the folding of each one, right? So the latency from start to end for one load is still 60 minutes, but the throughput now, because of pipelining, has gone up to 3 loads per hour from 1 load per hour. Okay. So the pipeline throughput is proportional to the number of pipeline stages times the unpipelined throughput, right, in the limit. So if the pipeline, in this case, pipeline throughput would be 3 times higher because the pipeline is 3 stages deep. Okay, so what does this mean in hardware? Well, in real hardware, it doesn't work out as well. So if we can see this, but I'll demonstrate that by looking at this design here. Here's a simple design that has an input register, an output register, and a combinational logic block. We'll assume that the delay through this combinational logic block is 8 nanoseconds, and that the time setup time plus clock to Q for these flip-flops is 1 nanosecond. Right? So from that, we know that the maximum clock frequency is going to be the 9 nanoseconds, because we're 1 nanosecond overhead for the flip-flops plus 8 nanoseconds to get through the combinational logic block. So the frequency would be 1 over 9 nanoseconds, or 111 megahertz. So if we wanted to pipeline this, if we could, we would put a register right down the middle of this combinational logic block. Right? So we put, let's say, half the logic on the left, half the logic on the right, and everywhere where we crossed a wire, we'd have to put a flip-flop in there. Okay, so there's some width to these wires here. Now, here we're assuming we can split this evenly, so we have 4 nanoseconds for CL1 and 4 nanoseconds for CL2, and put a register in here. So if we look at the time now to get through this functioning, the total CL, right? It would be 4 nanoseconds for this block plus 1 nanosecond overhead for that pair of registers, and then 1 nanosecond overhead for this pair of registers plus that 4 nanoseconds. So we'd have a latency of 10 nanoseconds. So as we can see, the latency of that operation actually went up. It got worse because of the overhead involved in this extra register here. However, the clock frequency now, the critical path is shorter because the critical path is from register to register in this example, right? And whereas before it was 9 nanoseconds, now it's going to be 5 nanoseconds, right? So frequency goes up to 200 megahertz. All right, so the CO block produces a new result every 5 nanoseconds instead of every 9 nanoseconds. So one of the things that happens with pipelining, though, is, as we said before, ideally, without the flip-flop overhead, and that's what I mean by ideally, the throughput improvement is proportional to the number of pipeline stages, right? So you can see we put it in 2 pipeline stages here. We almost doubled the clock frequency, but not quite. It went from 111 to 200. It didn't go up to 222. Right? And that's because of the overhead of the registers. So the register overhead somewhat takes away from the advantage of pipelining. Right? And you can see that in this plot here. Right? So the ideal speed up curve is the dashed line here. And the actual speed up that you get in this example here, with the numbers that I gave you there, you can see as you increase the number of pipeline stages, the clock frequency still goes up, but you get to a point of diminishing returns. It kind of begins to flatten out here and will asymptotically approach some limit. At this point, with 8 stages, because of the numbers, the ratio of the delay through the combinational logic block and the flip-flop overhead, once you get to 8 stages, half of the clock period is just in the flip-flop overhead. Okay, if you kept pipelining at more and more stages, after this point, the cycle time is dominated completely by the overhead of the flip-flops. Right? Yeah, so that's just something to keep in mind. There's some limits. If you make your pipeline stages too small, then the delay, the performances will be highly determined by the overhead of the flip-flops, the setup and the setup and time and the clock to queue time. Okay, so so that's the kind of main limiter to the effectiveness of pipelining. There's other things that sort of limit the effectiveness of pipelining. One is that the clock skew contributes to the clock overhead. So yeah, so that just means that the clock overhead is actually going to be worse because of clock skew. As we'll talk about this later in the semester, don't worry about that now. The other is uneven pipeline stages. So you see here, we could nicely divide this into 2 stages, each with 4 nanoseconds. But depending on what's inside here, you might not be able to divide it evenly, okay? Because you get to a point where you're going to have some kind of imbalance, most likely, because you can't divide exactly down the middle. Okay, so that will kind of limit. Maybe we can't get this to, maybe one would be 5 and the other would be 3, right? And then, of course, the critical path is going to be dominated by the 5 side, not the 3 side. So that would degrade, because you have to take the worst case. That would degrade the frequency, right? Or make the period longer, right? Also, as you pipeline to smaller and smaller stages, you have to add more and more flip-flops, and that becomes a cost to the implementation. So it may get too expensive after a while to keep adding more and more registers and flip-flops. Right? And then as you add more flip-flops, you have to distribute the clock to those flip-flops, and that consumes more. There's more power consumption associated with clock distribution. Right? And then kind of the big one, and perhaps the most serious one, is feedback. That's meaning when we have dependencies between loop iterations. Now, we saw that with CPUs. In CPUs, we call this a data hazard. That's when one instruction depends on the results from the previous instruction, right? And in our simple pipeline, we had a way to fix that, but it's not always fixable. So it could be that we can't start the next iteration until the one before it finishes, in which case it's going to limit the amount of overhead or the amount of overlap that we actually get between iterations. And I'm going to talk more about that now. So here's an example of a simple circuit that does a computation. Here's the computation up here on the left. This is a streaming computation. And what by that, what I mean, X is a stream of numbers and Y is a stream of numbers. You can think of them as integers or floats. Doesn't really matter right now. And inside this box, there's this calculation. So we're going to do some constant A times X squared plus some constant B times X plus C. So A, B, and C are constants. X is the input. So this is calculating this polynomial. And it, maybe it's useful for you somewhere. You're building a chip, you need to do this computation. Numbers are streaming in. So you can imagine a circuit that would do that. So here's a circuit that would do that with X squared here. So we take X and put it into this multiplier here, which multiplies it by A, so we get A times X, and then we go into this one and we get A times X, so that's A times X squared. Over here we get B times X. The results of those two things go into an add here, and then there's a final add here where we add in C. Okay, and then this repeats. So that's why the subscript here y sub I is a function of X sub I and these constants. And then we'll put a new X in, and then we get a new Y out. Okay, so this is a loop. It's just looping constantly over the input. Now, simple, we want to think about pipelining this. Well, we can just kind of cut it into stages, sort of like what we did with the processor. And, you want to think about how to cut it to get somewhat balanced stages. And we'll see later, but multiply is significantly more complicated than add. So sort of arbitrarily here, I just decided I'm going to put these two adders in one pipeline stage and then put a pipeline stage with them, those two multipliers in parallel, and then this multiplier in its own pipeline stage. So this would be a three-stage pipeline. But to actually figure out the exact best place to pipeline, you might want to do some analysis of the delays through these blocks, of course, and kind of get things as balanced as possible. Now, I put the question here, can we pipeline the basic operators? Yes, it's somewhat common in this type of computation to pipeline the multipliers. And in a couple of weeks when we talk about circuits for multiplication, we'll talk about how we can conveniently pipeline multipliers. Adders, we can pipeline too, and I'll show you on the next slide how we do that. We typically don't do it, but I'm going to show you it because it's a nice example of, another example of how to pipeline a circuit. So here's a ripple adder. You can see it here. This is a four-stage ripple adder, as we've talked about earlier in the semester. And we could put a pipeline. Now, the problem with the ripple adder, as you know, it has this long critical path that goes, the carry path that goes through all the cells. Right. And so if we want to speed up the operation of this adder, we might want to put a pipeline register as shown with this dashed line here. So cut all those lines. Right. And it ends up looking as drawn here on the right side of the slide, where you could see we put a register on all these input values here, put a pipeline register on the carry between those two stages, and then we put a pipeline register on the outputs. You can see what these registers are doing. They're synchronizing the data with the computation, right? So at some time, we put in all the A's and all the B values. the low A and B values go into these full adder cells. The high A and B values go into these registers, and they just wait. And they're going to have to wait for the next cycle before they're used. That's why we have a register here. So in the first cycle, we compute the sum outputs, and they get stored in the flip-flops. And we also compute the carry out of this half of the adder, and that gets stored in that flip-flop. And in the second cycle, we take these stored input values here and put those into these full adders along with that carry value and compute the sum. While these outputs here just sit in those registers waiting for these ones to come out. So everything comes out the next cycle. But when we are doing this calculation in the second cycle, we can start putting new values in at the same time so we can overlap everything. So that's how it works out. This cuts the critical path in half. You'd expect this adder to run at approximately twice the speed, minus a little bit because of the flip-flops. The cost is increased a bit because we had to add these registers in here. Right. This is a fairly simple circuit, so the overhead in cost of adding registers is significant. But if this were a big, expensive circuit, the incremental cost of adding registers would be relatively small. So this is possible for ripple adders. It's usually not done. In fact, next week or the week after, we're going to talk about how to make fast adders. And there's actually much better ways to make adders go fast than pipelining them, because it's usually important to have arithmetic unit produce a result in one clock cycle. If you think about how it's used inside a processor, it helps you understand why. You really want to be able to get a result every clock cycle. That way, I have a latency of only one clock cycle to avoid other kinds of hazards in the pipeline. Okay, so that's a simple example with a pipelined ripple adder. So now we're going to talk about some other circuits, and these is similar to the streaming example I had before, but except this one has feedback. We could call this a loop carry dependency, meaning there's a carry from one iteration to the next. Right? And this is actually popular. There's lots of cases where this comes up. Here I've shown you an example. This one equation here where you say y sub I is equal to y sub I minus 1 plus x sub I plus a. Right? So this is a recursive computation where y sub I is a function not just of the input x, but also of the previous result. Right? And this being a function of the previous result, that's where the loop comes from. We have a dependency. Y sub I is dependent on y sub I minus 1. Okay, this comes up in signal processing, digital filters, and other computations such as that. If we built a computation graph for this, it would look as shown here on the right. It's not unique, but this is one version of it, where we have the output here, y sub I, and we need to take the output from the previous previous iteration and store it and use it on this current iteration, right? So if we take y sub I and we put it into a register, what we see on the other side of the register is y sub I minus 1, right? Because on each clock cycle, we're basically just delaying y sub I by one clock cycle so that it can be presented along with x sub I. So when x sub I comes in, we have y sub I, which is the result from the last time around, sitting here. So those get added together, and then we can add a in, right down here, and that produces the new result. So we just keep clocking that, putting in new x, and get the new y's out. So if we look at the kind of schedule of this, how this executes in time, here's an unpipelined version here. So we need two adders. So I'm going to look at the use of each adder, right? And they're both operating on the same clock cycle. So we're going to put them in the same column here. So in the first part of the clock cycle, we use adder 1 to calculate x sub I plus y sub I minus 1. And the second part of the clock cycle, later in the clock cycle, because this is just going to kind of propagate through here, we'll calculate y sub I, which is going to be a plus this stuff up here, right? And then on the next clock cycle, we repeat that. Okay, so this is just on pipeline. So what if we try to pipeline this? Well, we can cut this. Can we feed pipeline that? That's the question. Okay, so we'll try that. We'll put a register in between here and see what happens. Well, what that would cause to happen is that on the first clock cycle, we'd calculate x sub I plus y sub I minus 1, and then the result would get stored in a register here. And on the next clock cycle here, the next column, we calculate y sub I, right? And then that would go into this register here. And then on the next clock cycle, we could start the next iteration. So we can't really overlap the iterations because of this, the dependency, right? The extra register doesn't help in this situation. It actually hurts because it kind of spreads this. It's going to increase the latency of this. So this is the general problem. We can't effectively pipeline feedback loops. Right? This is very much like the data hazard problem that we had in the CPU, right? We had this dependency, which we thought initially wouldn't allow us to overlap instructions, but we found a way to make that work in that case. There's no easy fix in this case, right? So we'd end up with this wasted time. So at every cycle, we'd only be using one or the other adder. So we probably wouldn't want to do that. What can we do? Well, we can't overlap we can't overlap the iterations because the dependencies, but we can rearrange things a bit, right? We can overlap the non-feedback part of the iteration. So add is associative and commutative, therefore we can reorder the computation to shorten the delay of the feedback path, right? Since the feedback path has to happen all in one clock cycle, we can't split that across clock cycles. What we like to do is make the feedback path, which will determine the critical path of the circuit and will determine the maximum clock frequency. We want to shorten the critical path as much as possible. Therefore, we can reorder the computation to shorten the delay of the feedback path. And I've shown here how to do that. We just reassociate and commute. So we're going to do, what we can do is first add a to x, and then add y sub I minus 1 to that, right? So that takes this computation graph and turns it into this one here, where what we've done is kind of factored or moved out the x sub I plus a here. And then this is the part where then we take the result of that and we add in y sub I minus 1. So now the feedback is short. There's only one. Before, the feedback path or the critical path was through 2 ladders. Now the critical path is through a single ladder, right? So that helps by pulling out the non-feedback part of the computation. And then the computation graph kind of looks like this. On one clock cycle, we can do x sub I plus a. And the next clock cycle, we can start the next version of x sub I at the same time, and we can do this this add operation with the feedback, right? So we get to overlap somewhat, but we can't pipeline the feedback, but we can still overlap computations. Okay, unless we're going to pipeline this add operator, the pipelining is limited to 2 stages in this case. Okay, so that's one thing to keep in mind about when you have loop carry dependencies. Now here's another example here. This one's a little tougher. So this example is y sub I equals a times y sub I minus 1 plus x sub I plus b. So similar to what we had before, except we're multiplying a constant times the feedback value. So if we took this and directly implemented it, we'd get a computation graph that looks like this, where here's our result. It goes out. It also goes into a register for the loop carry dependency or dependence. And then there's y sub I minus 1. So that's going to go into a multiplier times a, and we add x sub I to it, and then we add b to it, and that gives us our result. Okay, so that's going to loop. All right, so we'll do the same trick that we did last time. We pull out, reformulate this equation so that the B plus, excuse me, the B plus X sub I part we can do on one clock cycle, and then the next clock cycle we can do this feedback. Now we still have a long feedback path, so maybe we would be tempted to try to put a register in here to break this up into multiple cycles, right? And you really wouldn't want to do this, but I did it here for a purpose, and I'll show you why in a second. If we did do that, okay, so how would this execute? Well, on the first clock cycle, the first stage would be the B plus X of I. That would be this adder here. This multiplier could do Y sub I minus 1 times A, and then that gets stored in, imagine you have a register here. And then on the next clock cycle, we could calculate these two register values, this one here and this one here, would go into this adder, and we could calculate Y sub I. And then as before, we really can't overlap this next iteration, so the Y sub I then is needed for this next calculation here. Right? In the meantime, we can do that, and then this is needed for this. So we get this kind of dependency chain. That's why this computation gets spread out in time like this. It's because of the dependency. So we still need 2 iterations, 2 cycles per iteration. So what could we do with this one? Well, there's a technique called C-slow, and you'll see why we call it that in a minute. But this is an approach to increasing the throughput in the presence of feedback. What we can do is fill in the holes in this computation schedule, or in this chart, with another independent computation. Right, so if you look at it, these spaces in here where nothing's happening, that's wasted resources. Right? That shape of that matches the shape of the computation that we're doing. Right? So if we had another independent stream, we could compute it in this hardware, in these empty spots. Right? We could drop down another computation in those empty spots. Okay, and we say we interleave it with the first. Right? So when does this come up? Well, if we had 2 different equations, but they have the same function, they just happen to be working with, in this case, let's say they even have the same A and B values, or maybe those could be looked up and changed on a per cycle basis. But anyways, 2 streams of numbers, X to the 1 and X to the 2. These are not powers. This is just designating 2 different streams. We have F1 and F2. We have X1, X2. They're both iterating. Right, so you could think of possibly like left and right channels of a stereo. Right, you're doing the same, or a sound stream, where you're doing the same computation on the left and the right. Right, so what we could do is then instead of implementing this as 2 separate pieces of hardware, we just implement one of them in the way I've shown on this last slide. Right, and then we can interleave the second computation in between the first. Right. So here the feedback depth is 2 cycles. That's what the C means. We're slowing down the computation of each one, right, by a factor of 2. So each loop has a throughput of the clock frequency divided by C, in this case divided by 2. But the aggregate throughput is going to be 1 result per clock cycle. It's just 1 result be for the left, and then the next result will be for the right, and then left, right, left, right, left, right. Right. So with this technique, we can pipeline computations that have loop carry dependence, assuming we can supply C independent streams. Right. So essentially, this means we could go ahead and cut the feedback, as I said, right, and then and map the 2 different computations. So we've got let's imagine the white one here is going on, and then the colored one is going on in between. Right. So this really, what we're doing is making operations in the adjacent pipeline stages independent, and that allows a full cycle for each. Right. The streams must be independent. Then you have to have an input mux that interleaves the input streams. The mux will take from the left stream and then take from the right stream, then left, then right on alternating clock cycles. And then, as I said, each stream runs at half the pipeline frequency, but the pipeline achieves full throughput. So it makes our use of the hardware efficient. Right? And it kind of spaces out each computation in time so they don't have these hazards that come up. Okay. So this technique is called C-slow. It's similar to a technique that multi-threaded processors use. So modern processors, again, this is something you'll learn about in 152 if you're interested, is the modern processor will interleave different programs or different threads in a single CPU to kind of spread out the dependencies within a single stream and make it easier to deal with hazards. Same idea as here. Okay, so that's C-slow. So that's pipelining, and the pipelining is a pretty powerful thing because I don't know the right picture for that, but we get a very good at performance improvement for a very small increment in cost, right? This could be a fairly expensive computation in terms of space. Multipliers are big, adders are fairly big. Registers are relatively small, right? So we increase the performance of this circuit by approximately 3x for a small increment in cost, right? So it's a very good trade-off between cost and performance. Right? Now there's some limit to how much performance improvement you can get for pipelining for the reasons that I mentioned earlier, right? But when you can use it, it's a very good technique to use. So typically we do that first. So when you think about finding ways to optimize for performance, pipelining in hardware design, pipelining is the first thing that we apply because it comes at relatively low cost. After that, beyond pipelining, then we think about what I'm calling SIMD parallelism, which is single instruction, multiple data. It's really data level parallelism where we duplicate function units. Right? So if you have loops, again, talking about loops, an obvious way to exploit more parallelism from loops is to make multiple instances of the loop execution data path and run them in parallel, sharing the same controller. So for instance, these computation graphs, as I shown here, you can think of this as a hardware implementation, and you put another one of those and another one of those. And as long as you can keep these inputs coming at high enough rate, you can keep them all busy, and you can get, each one represents an iteration. So that's one iteration, second iteration, third iteration. And then the fourth iteration will get mapped here, and the fifth iteration here, and then the sixth iteration here, et cetera, et cetera. Right. So that's the idea of kind of parallelizing loops spatially, and not with pipelining. So P instances, the throughput would improve by a factor of P. Right? So here's an example. You have y sub I is equal to some function of x sub I. You could just duplicate 4 times f, right? So you just duplicate that data path, right? In order to make this work, it assumes that the input rate is high enough, right? So it assumes that 4 x values are available all at once, right? And this assumption, whether or not it's valid, it depends on the ratio of the f repeat rate to the input rate, or the memory bandwidth if this is coming out of memory. Right? The cost of this approach, unlike pipelining, where what I said was very efficient in terms of its cost, this is much more expensive because the cost is proportional to P, to our replication factor, right? And this is usually much higher than pipelining. However, it provides can provide a high speed up. So often this is applied. It's applied after pipelining. Now, by the way, vector processors are SIMD units, like MMX or SSE. Well, it used to be called XSC, SSE, and then it was MMX, and I forgot, AVX, I think it's called in Intel processors. These are the special vector instructions. Those get executed in a way similar to this. Right? So the vector add instruction adds a bunch of elements in parallel. So there's a bunch of adders that are all in parallel. And there's a big vector register that holds all the elements of the vector, and they go through all these adders. Right? Once again, though, the effectiveness of this technique is limited by loop carry dependencies. Feedback translates to dependencies between these parallel data paths. So I can show you an example. Here's our example earlier that we had. Y sub I is equal to A times X sub I minus 1. That was the feedback one, plus X sub I plus B. So if you unroll this loop spatially, which I'm suggesting here, so you've got one data path here that's responsible for calculating Y sub I. And then this one would calculate Y sub I plus 1. Right? So that would take as its input X sub I plus 1, and then A and B. And of course, this iteration is dependent on the previous iteration. So that loop carry dependence turns into a wire. It used to be a register. Remember, I told you before that wires in space turn into registers are wires in time, right? So before we had this connection, which here is in space, in the serial one that we're executing the loop serially on one piece of hardware, that one was, we had a register in there to make that connection. Here is just a wire. Okay, and then that generates a Y sub I plus 1, and then that value goes into this iteration, right? So then we could take, if we had this iteration that goes for, this loop that goes for many, many iterations, we'd take the first 3 and map it on here, and then the next 3, and then the next 3. So it would decrease the total time required to do the computation by a factor of 3, because we've increased the throughput by 3x in this case. However, this loop carry dependence creates a long critical path here. This is a long combinational path to all these 3 blocks. This is similar to what happened with the carry ripple adder. Right? So now we're going to talk about later, not today, if these operations are associative, we can kind of use a tree type structure to reduce the delay here. Remember, we talked about if operators are associative, then we can do kind of a tree way to do a reduction. You can think of this as sort of a reduction, and we can use a kind of tree to speed it up. We'll talk about that later. So we can do something about this loop carry dependence and the fact that it creates a long combinational path delay here. But that'll be for some other time. Okay, so that completes this part on parallelism. Anybody want to say anything? Oh, okay. All right, so move on to a new topic. So this is lecture 16, and this one is really all about a big design example. So we're at the point in the semester where I think it's useful to see a lot of the things we've been talking about kind of come together in a large example. And it's fairly realistic, but it's small enough that we can do it in one lecture, although I'm not going to finish it today, obviously. Finish it next time, but it kind of ties together a lot of things we've been talking about and introduces a couple other things that help when we think about how to do digital design. And so the example is this piece of hardware that processes lists stored in memory. And I'll show you about that in a minute. Before we do that, though, I want to talk about something I call register transfer language. Right. So back, kind of a review of our abstraction of digital systems is we have combinational logic blocks and we have registers, and they're connected together in some way. And at the high level, we view this is really our view of the system. Then we can dive inside the registers. We did that, and we can dive inside combinational logic, and we can do that. But at some level, we can abstract things this way. It's a nice way to think about the organization of systems. So this level of design people call, I think I mentioned previously, they call this RTL, or register transfer level. Because you think about the operation, and every clock cycle we move values from one register to another, or from the input through a combinational logic block into a register, or from a register to the output, or, like I said, from a register to another register. But in the process of going from register to register, we move through the combinational logic block, and that's where the real computation happens, of course, or at least the operations. Right. So this leads us to think about this as a register transfer level description of our circuits. Right. It abstracts away a lot of the details, and that's nice. It helps us think about the data, the movement of data through the system. Now, to not be confused, some people call RTL Verilog or VHDL code, and it's strictly not correct. But if you look, most Verilog or VHDL that people write, they write it sort of at this level where they use a behavioral description of the combinational logic blocks, and they use a structural description of connection of combinational logic blocks and registers. Right. So therefore, it kind of takes on a very register transfer level-ish description. Right. So people call, in industry, they often call Verilog or RTL, VHDL code RTL. I'm going to introduce something similar to this, a language, a different language is not Verilog or VHDL. It's a special language that's used just for describing these register transfers. Okay, and it's something I've made up and other people have made it up, and it's never really been standardized, but I think it's helpful in describing digital systems. So I'm going to introduce this language for describing the behavior of the systems at the register transfer level. Okay. As I said before, we can view digital synchronous systems as a set of data transfers between registers with combinational logic operations happening during the transfer. So I'm not going to call this RTL because that really is used for register transfer level description. I'll call it RT language, right? When I do need to refer to it by name. So this is what makes up this language is a set of register transfers with optional operators as part of the transfer. So here's an example. We could say transfer register B to register A. Right? The contents of B moves to the register A. Right? Or here, move into register C the value of register A plus the value of register B. Right? Or a plus operator there. Or something like this. If start equals 1, then register A gets the value of register C. Something like that. We could have ifs too. Right. So it's not a formally defined language, but I'm just going to make it up to help in our examples here. So what I do, we use Semicon to separate transfers that occur on separate cycles. Right. And then a common to separate transfers that occur on the same cycle. So here's an example. Here's 2 cycles, because here's the first set of transfers here, separated by a comma. So they're supposed to both happen in this clock cycle. And then we move on to the next clock cycle here and do this transfer. Okay, so every line that's separated by a semicolon is a new clock cycle, right? And every transfer that's separated by a comma is going to happen at the same time. So these happen in parallel. and these happen sequentially. Okay, so here's an example of using an RT language here. In this case, the language description is used to sequence the operations on the data path, right? So this becomes a high-level specification for the controller. So let's say we have this data path here, and then we have this language description here, right? This is used to specify a set of transfers that's happening here. For instance, we can say this accumulator gets accumulator value plus R0, right? And at the same time, R1 gets R0. Well, we know we can arrange that to happen because the accumulator value feeds back into this adder. R0 is here, so if we set S2 to be 0, on this clock cycle, this value is going to flow here. Of course, this value is flowing around here. And then we enable the accumulator clock enable on the rising edge of the clock, it will get the new value, which is ACC plus R0, right? At the same time, we can enable things so that R0 goes to R1. So R0 is here. It's going to come here, and then we can go to this mux around here, and we can clock enable R1 and set these two muxes to route the signal to the proper place. So you can imagine for each kind of statement here, we'd have one clock cycle, right? And for each one, we could figure out a controller how to activate these control points to get these transfers to happen appropriately. So this would lead to a finite state machine, right? That would kind of loop, or not, but a finite state machine that would sequence through the set of operations where each one of these would be one state of the finite state machine, and we would move from state to state on each clock cycle. Right. So that would be a use for this RT description here. It gives us a way to describe the function of the controller. Once we describe it this way, then it's a relatively straightforward process to go from this into a state machine. Once we have the state machine, we know how to design hardware for that. So this language description gives us an effective way to go to abstract and think about the controller design and make sure we have it correct. And then methodically, or kind of step by step, go from that into an actual hardware description of the controller. Sometimes the language could be used as a starting point for not just a controller, but both the data path and the controller. So here's an example here. I say reg A gets in, reg B gets in, then reg C gets reg A plus reg B, and then next cycle reg B gets reg C, right? Now, if we look at this, we can deduce a lot of things. And in fact, we can use this to figure out what the data path and what the controller would be for a piece of hardware that executes this function. Assuming this were important to you, you may want to go through this process. So we can deduce from this, look, A goes to both register A and register B. First of all, we need 3 registers. If we analyze this, register A, register B, and register C. We also know we need an adder because we have an add operation here, right? So over here, what's the data path look like? Well, we know we need a register A and a register B, so we'll put those here. And then we know that in goes to both A and B. So we can take input and fan it out, right? So I'm assuming there's clock enables on these registers here, so we can choose whether in goes to A or in goes to B, right? Register A and register B must output to an adder, right? Because we're right here. We're adding these 2 register values together, so we know we need an adder in here. So we put the adder in here. And then we know that the output of the addition goes to register C, so we put register C there and wire that up. And then from here, register C gets fed back into B. Right? So we need a wire that goes back like that. And then we're kind of in trouble here because the input to B is already occupied. And of course, we know how to fix this. We put a multiplexer here. So in this clock cycle, we're going to choose from the feedback path. But on this clock cycle up here, we choose from the input. So we'll take that out and replace it with something that looks like this. So we have multiplexer here and another control point. This allows us to take, missing the connection between the mux and B, but there's an output here that somehow disappeared. Okay, so that was good. I mean, we were able to deduce the data path based on this little program here. Now, by the way, this is very similar to what we did when we were just designing the RISC processor. We looked at the action required for each instruction, and we built the data path according to that instruction. It was a little more complicated in that case, though, because as we added more and more instructions, we had to add more stuff to our data path and more control points in order to differentiate one instruction from the other. So that would give us the data path. If we wanted to implement the controller, then we'd have to figure out what the control points are here, right? So we have clock enable for register A, clock enable for register B. We have clock enable for, and then we have a mux control point here. And maybe not a clock enable for C. I don't know that we need it in this case. We could just automatically load it every clock cycle. So that would be the first part of the controller. And then once we had the control points, we could make a finite state machine. In this case, it would have 4 states, 1 state for each clock cycle, that would set the appropriate control points to make this transfer happen. So for this first clock cycle, we would enable register A, but not enable register B. Right? We'd have a don't care for the control of the multiplexer because we won't enable clock B, register B. Right? And so the finite state machine could go through 4 states and it would do this computation. And if it were streaming, then we could just repeat that. We'd put that into a loop if we had a stream of input values. Okay, so that's kind of a nice way then. If we can come up with a little program like this, we have a technique to turn that into a data path and a control. So we have a technique to make this into a little hardware engine that can execute that. Now, it may not be high performance, as we'll see with my bigger example, and we'll probably get into optimization next time. But once we have this, then we can think about how to optimize its behavior through pipelining and parallelism or something like that. Okay, so in the remaining 12 minutes then, I'm going to start the example. And I went through this preliminary material because we're going to use this idea of an RT language program to do our large design example. Not too large, but it's large enough to be interesting. Okay, and this is a list processor. Here's the example. I'm going to start now. Okay, so before I do that, I'm going to again back up a bit and say the RT language gives us a framework for making the high level design and doing optimizations, as we will see. So the general design procedure we're going to follow here is you start out with some problem specification, some constraints on its implementation in terms of how expensive it can be in terms of number of components or number of transistors or number of logic gates or number or something like that, some measure of cost, a constraint on how much power it can consume or energy per operation it can consume, and then some constraint on its performance. What should the clock frequency be, or what should the number of operations per unit time be? And then usually some component library specification, a set of blocks that we can use for implementing that design. Right? And that set of blocks depends on what your implementation technology is. If it's an ASIC, you might have standard cells. If it's on an FPGA, you might have LUTs and flip-flops and RAM blocks. Once that's the first step, okay, you're given that, and then we have to choose an algorithm, which is a kind of the program, so to speak, or the algorithm to solve this problem. Okay, From that, it'll lead to some microarchitectural specification. It's kind of like data path plus control, similar to what we've just done in these examples. Once we have that, we'll have the real implementation, and we have the specification of the component library. So based on the components and their interconnection, we can figure out what the cost is, and what the performance is, and perhaps what the power is. Right? And we can check to see if that meets our constraints here. If it doesn't, then we want to do some optimizations somehow, massage the design, maybe pipeline it, or use parallelism, or use something else to make some variations on it. And then do the detailed, then kind of repeat, kind of go back to this step 3, and then do another analysis, and we kind of iterate around in here. Right? If we can't get to where we need to be, maybe we have to change the algorithm, right? Or maybe we have to push on these constraints and say, well, it's not possible to do it with that amount of power or with that amount of cost, right? And then we can do a detailed design once we get to a point where we think we have the right microarchitecture. Okay, so we're going to try to follow that technique with our design example here. So here's the problem specification. It's number 1. We want to design a circuit that forms the sum of all the 2's complement integers stored in a linked list structure, starting at memory location. The structure starts at memory address 0. All right, so here's a linked list. You've seen these in 61C or other classes. A linked list is a data structure that gets stored in memory, where the top half, there's a set of nodes. Each node has, in my way of building them here, has a top half of the node is a pointer to the next node. That's what keeps it linked up together. And in this simple example, we're going to just have integers in the second half of each node. Right. So we're going to say this first node is at location 0 in our memory. There's some memory block here. The last node of our linked list, and this can be arbitrarily long until we fill up the memory. The last node is going to have a null pointer here. A null pointer is just represented as a 0 here, so it doesn't point anywhere. Maybe you can think of that as pointing back to the beginning, I don't know, but think of it as a null pointer. That ends our list. You can see how that one such list is mapped into this memory space here on the right. There's the first node that holds its pointer is a 5. It points to this location 5. Has another node, there's a different X here, that's X1. Its pointer points off to this node, X2 is stored here, the next memory word, and then that points here, and then this is the last node, it has a 0 here. So this list is 4 nodes long. For our example here, to keep things simple, we're going to assume that all the integers and the pointers are 8 bits. Right? So 1 byte wide. So the linked list is stored into a memory block that has an 8-bit address port and an 8-bit data port. Right? So this is a relatively small memory. 8-bit address port means we can only have 256 locations, but I just want to keep things simple for now. We'll assume that there is at least 1 node in our list, just to keep the hardware simpler, right? So this is kind of an abstraction of what we want our list processor to look like. We're going to add a start signal that when we assert the start signal on the rising edge of the clock, it initializes everything and starts the process, right? And this is the processor, so it has the process of following the nodes. What it's going to do is follow all these nodes and add up all the X values, right? Because that's what we want to do, and add up all these integers. And when it's done, the list processor asserts the done signal, and the result appears on the R result signal here, this R output that's 8 bits wide. For it to do its job, it needs a memory here. So we'll assume there's a memory, and here's the 8-bit address. And you put an 8-bit address in, and there's a 8-bit result that comes up. That's asynchronous memory. This note here, we don't assume that the nodes are aligned on 2 byte boundaries. Right? So in fact, here's not a 2 byte boundary. You could make things simpler by making the nodes aligned to 2 byte to only appear on even addresses, but we won't do that, just to keep things a little more challenging. All right, so that's the specification of the problem. Okay, it's just we want to figure out how to build an engine that follows these linked lists and adds up all the integers. Okay, other constraints. So that's the problem specification. The other thing is we would probably, in the real world, we would get some specification that puts a restriction on the cost and the performance and the power, or all of those. We're going to leave this unspecified for now. We'll return to this later. Here's the component library we're going to use. These are kind of, well, these are the numbers. They're kind of just made up. They don't correspond to any real circuits, but I think they're somewhat realistic. We have simple logic gates, and we'll assume each logic gate has a 0.5 nanosecond delay through it. So we need these actual delays so we can calculate the performance of our implementations and use those as a way to guide our optimization to get more performance. And I'll show you how we're going to do that later. N-bit register, we're going to assume the clock to queue time is 0.5 nanoseconds and the setup is 0.5 nanoseconds. The multiplexer, we're going to assume a 1 nanosecond from any input to its output. N-bit adder, we're going to assume is 2 log base 2 of n plus 2 nanoseconds. Memory, we're going to assume is 10 nanoseconds, and it's asynchronous read. And a zero compare, which we will need in order to terminate operation, we'll say is 0.5 times log of n. So before I show you the first implementation of this processor, we can ask the question, are these delays reasonable? Right? And we should be able to answer that based on what we know so far. Logic gates, well, we just made up a delay for that. But if you look at a register, you notice this n-bit register and these clock to queue and the setup time is not a function of n, right? And we know this is true for registers, right? It's just a property of the flip-flop. It's not a property of how many flip-flops we put in the register. Okay, so that could be reasonable. N-bit register, n-bit 2-to-1 multiplexer. Again, the delay won't be a function of n because the n-bit multiplexer is just a bunch of multiplexers in parallel with one another, right? So there's no dependency between the bits. So this should not be a function of n. And it should be more than a gate delay, right? You can do this with a couple gates, right? So I just said 1 nanosecond, okay? Just for, it's kind of made up, but it's somewhat reasonable. Look at the adder. Okay, so this assumes not a ripple adder. If it were a ripple adder, the delay would be a function of n. Here it's a function of log n, right? Which kind of shows you a little hint into what we're going to see in the future. We're going to figure out how to build adders that have a delay proportional to log of n, right? And that will come up in a couple of weeks. Memory, 10 nanoseconds, somewhat reasonable. And zero compare. Now, zero compare, we talked about this before. I think maybe we had a problem in the midterm or homework about it anyways. And this ends up being a bunch of XOR gates and some sort of tree reduction, right? So you'd imagine it would be a delay proportional to log of n, and there'd be log of n logic gates in the critical path. So it'd be something like 0.5 times log base 2 of n. Something like that. Okay, so yes, these are reasonable. And it's 5, so I'm going to just, a little more backup. All right, so I think we're going to have to quit there, and I will continue this next time. And next time we'll start out, and I'm going to just show you a little bit of what we're going to do. We're going to write a program in this register transfer language that has the behavior that we need in order for this list processor, and then we will go from this program to a data path plus the controller, right? And then we'll go through a series of optimizations. Okay, so that'll be coming up next week. So we'll do that next Tuesday, and I'll see you then, and have a good weekend.
Thanks, Professor.
Okay, thank you.
Thank you.
Bye-bye.
Thank you. Bye.
Bye-bye.
Bye.
I'm gonna stop. I have to stop the session to stop the share, the recording. Quincy, I'll be back. I'll start it up in a sec. I just need to end this one.
Sounds good.
Well, actually, what I'm going to do, I'm going to start up another one, my personal one. So I'll send you email with that link.
All right.